So hello everyone, thanks for coming by. Today we're going to talk about the Optimum-Path Forest classifier. Uh, Actually, the OPF is not only one classifier, it's a framework, as we are going to see today. I don't know if we have several variants of the OPF. Today we're going to talk about the very first one, and then we can also extend it to different variants of the OPF. Okay, so let's get started.
So, as I told you, we are going to talk about the optimum path forest, okay, also known as OPF. Just to make it clear, the OPF is not only a single classifier, in fact, it is a framework, okay? It's a by framework, I mean, depending on the configuration of the OPF, you can design your own OPF classifier. So today we have supervised, semi-supervised, and the supervised versions. And even when we are talking about the supervised classification, we have two variants of the OPF. But today we're going to talk about the very first one. Okay? So let's get started. Just to give you some very brief introduction about machine learning or pattern recognition. So basically we have a data set. Then, depending on the problem, we are going to have different features extracted from the data set in order to obtain a feature space, something like that. And then, when we are working with supervised classification, like suppose here we have a binary classification problem, which means I have two classes only, and basically any pattern recognition technique tries to find a hyperplane that can separate samples from different classes. So although the OPF tries to separate samples as usual, the OPF is a graph based classifier. So which means we are not trying to compute hyperplanes explicitly. I mean, we're not trying to find straight lines or hyperspheres and all these decision boundaries explicitly, but obviously we gotta separate the feature space, right? But basically, each sample of my feature space is gonna be represented by a graph node, right? And basically, by definition, a graph is composed of nodes which are connected by using some adjacency relation. Okay, we need to choose something. We need to choose some methodology to connect the nodes. And basically, the main idea is to somehow find a way to remove arcs among samples from different class, right? By doing that, we can just partition the graph into that we call discrete regions, okay? And then these regions will be some sort of connected components. So we are going to disconnect the graph in order to build connected components, and each component stands for a cluster, for instance, okay? A group of samples that's supposed to belong to the very same class, right? Okay, so that's the main idea of a graph-based classifier. So, as I told you at the very beginning of this lecture, the OPF is not only a single classifier, it's a framework, which means depending on the configuration of the OPF, you can obtain a different classifier. So, by configuration, I mean, when we are trying to design a new OPF-based classifier, we gotta choose three main things, right? As I told you, as we are working with a graph-based classifier, the first thing we gotta choose is the adjacency relation, right? As I told you, we have the graph nodes, and we gotta choose a way to connect the graph nodes, okay? And then, after choosing the adjacency relation, we have to choose a methodology to estimate the prototypes. So we're going to talk about that. But the main idea of the OPF is after we connect the graph by choosing the configuration here, number one, so adjacency relation. The OPF training algorithm basically it rules a competition process among prototypes. So basically, so imagining a prototype as the most important node from a given class. So if we have a C class classification problem, so we're going to have at least C prototypes, and each prototype, these guys going to try to conquer the remaining nodes of the graph, offering to them optimum path costs. So it's basically a competition process, and each prototype, so imagine that each prototype has its own influencing region, right? And the prototype is going to be like the most important guy of its cluster. So and at the very end of the competition process, we're going to have a partitioned graph. Okay, so we have the prototype estimation methodology, and finally, in order to offer like rewards to the remaining samples, I mean, when a prototype is going to try to conquer the remaining nodes, we gotta choose some function, some reward that we call the path cost function. As I told you, imagine it's a kind of reward we are trying to offer to the remaining samples in order to conquer them. Okay? So let's just roll back a little bit. So basically, the OPF has a training and a testing phase as usual, and the main idea of the training phase is just to start this competition process. We are going to end up in a partitioned graph. I mean, we're going to have a training set that's going to be partitioned into discrete regions. As I told you, we have like this kind of discrete regions. But basically, each prototype sample, suppose like this guy is a prototype, another prototype, and the prototype samples, when they conquer the other samples, at the very end of the training phase, we are gonna have optimum path trees. Okay, so we're gonna have optimum path trees, and each optimum path tree, each OPT, is gonna be rooted at each prototype, right? And basically each partition of the graph is going to be an optimum path tree, and the collection of optimum path trees gives the name of the classifier. That's called Optimum-Path Forest. Okay, it comes from the graph theory. So basically, now I'm gonna show you an example regarding the OPF classifier we are going to discuss today. So as I told you, we gotta choose these three main very important configurations, and then I'm gonna show you some numerical example showing the training phase of the OPF as well as the testing phase, okay? So, okay, let's get started with a toy example. So basically, so suppose we have this binary classification problem, okay? So we have two classes, the yellow ones, samples from the yellow class and samples from the blue class, and then we have the arcs between two different samples, for instance. So they are weighted by the distance between their corresponding feature vectors, right? It can be Euclidean distance, for instance. Actually, the default distance for the OPF is Euclidean distance, right? So basically, as I told you, we gotta choose three main things. So the first one is the adjacency relation, as I told you, and basically adjacency relation. So for instance, we have k nearest neighbors graph, k-NN graphs. We have a complete graph, that is some sort of full connectedness graph. I mean, each pair of nodes, these guys, they're connected by an edge. I mean, everybody is connected to everybody. So that's the adjacency relation we are going to choose for the very first version of the OPF. So which means we have like this complete graph here. Every node is connected to every other, and then we need to compute the distance between every pair of nodes. Okay. Well, that's the first thing. We need to configure the adjacency relation. And the second one, as I told you before, is related to the prototypes, right? So prototypes. The prototypes, they are the key guys of the OPF, okay? So basically, imagine it's some sort of analogy between the prototypes, the OPF prototypes and the support vectors of the support vector machine. So when we have some classification problem, so we have samples, and then most of techniques, they try to build the hyperplane around here, right? At the boundary of the classes, okay? Because that's the region we're going to protect, because we have samples from different classes, and in some situations they're very close to each other, which lead us to high probability of misclassification at that region here. So following the same idea, with OPF, the main idea is try to place prototypes in this region in order to protect, for instance, a prototype from one class trying to invade the space of the prototype from another class, right? So basically, so after we just create the adjacency relation of the graph, we gotta choose the prototypes, and as I told you, we are trying to protect the boundary of the classes. So which means we're going to choose as prototypes nearest samples from different classes, okay? But how can we do that? First of all, we need to compute the minimum spanning tree. So the minimum spanning tree is basically a spanning subgraph in which the summation, and this spanning subgraph, it's a tree, and the summation of the arc weights of these three is the minimum as possible, right? So that's the minimum spanning tree. It comes from the graph theory. That is basically we're going to find a subgraph that is a tree. I mean, it has no cycles, where the summation of the arc weights is minimum as possible. We can find a lot of spanning trees, but in this case we have only one minimum spanning tree, right? So the main idea of using a minimum spanning tree is that, as I told you, in the minimum spanning tree we force the arcs with like small weights to belong to the minimum spanning tree, which means that we are going to connect the nearest samples from different classes, right? So, as I told you, we have the graph, the original graph, and then we compute the minimum spanning tree over that graph, and then we can just like walk through the MST, and then as soon as we find connected nodes from different classes, we just mark them as prototype. Okay? So here, for instance, in our example, we have samples C and D as the prototypes, right? So in this case, we have only two classes, and then we have only two prototypes. But it doesn't mean that if we have two classes, I can have like more than two prototypes. The only requirement is that if we have C classes, we gotta choose at least C prototypes, because we need like at least one prototype per class. Okay? So after choosing the prototypes, we gotta now configure the last part, that is the path cost function. I mean, each prototype is going to try to offer a reward to the remaining nodes. I mean, each prototype is going to try to conquer the remaining nodes. And for the path cost function, in fact, we can use most of the path cost functions, but it needs to be smooth. It needs to obey some properties, but we are not talking about that properties today. But basically, our path cost function needs to be monotonically increasing. Okay, as long as we don't have arc weights with negative values, there are a lot of path cost functions we can choose. The most simple one, like it's very similar to the Dijkstra one, we call in the OPF papers fsum. That is basically the summation of the arc weights along a path. For instance, if I start a path from sample B and I try to go to sample C using the shape of the MST, I gotta just like take the summation of the arc weight. So I'm gonna be like starting from point B, and if I walk through point A until point C, we're gonna have a path cost function of .7. That's basically .3 plus .4. That is the fsum. But the problem with fsum is related to the chain. You know, the chain code problem. So imagine we have chain code, or just like chain problem. Imagine we have a sample like this prototype over here from white class, and we have a prototype from the black class. Okay, and then if I use the fsum, so this prototype here is gonna need to sum all arc weights until we get this very last guy here. So probably, depending on the length of the chain, the cost that this prototype here will offer to this sample here is going to be like much more, it's much greater than the cost that this prototype here that's from the black class, we're going to try to offer to this sample here from the white class. So probably this sample here is gonna be conquered by the black guy. So it's gonna be misclassified. So in order to avoid the Jane code problem, the first version of the OPF does not use the fsum. It uses what we call the fmax instead. That's basically the fmax. Instead of computing the summation of the arc weights along a path, we just take the maximum arc weight along a path. So for instance, if we start a path from sample B and we pass through sample E until sample C, the cost of these paths is going to be just 0.4 because we're using the maximum arc weight on the path. Okay? So the first version of the OPF choose the fmax as the path cost function. So for the path cost function, we use fmax. As I told you, it's not a big deal to design your own path cost function. Okay, you just need to obey some properties. It needs to be smooth. It needs to be monotonically increasing, and we are not allowed to have arc weights with negative values, right? So basically, after choosing the adjacency relation and also after choosing the prototypes and also choosing the path cost function, we gonna need to run the OPF algorithm, right? So basically, we're gonna just take an image here that is basically the output of the OPF. Okay, so after choosing the prototypes, I just come back to the original graph, okay, and I'm gonna start a competition process. So how can we do that? So the main idea of the OPF is to minimize the cost of each sample. So basically, what we have at the very beginning, we just associate the cost 0 to the prototypes, okay? And to the remaining samples, we associate them a very high cost. Okay, and we put all these samples in a priority query, and then we are going to extract the sample from that priority query with the smallest, with the lowest cost, right? So by doing that, we can guarantee that the very first samples that are going to come out of the query, they're going to be a prototype. Okay, so suppose we have like this priority query over here, so something like that. Sample B, sample C, it's a prototype, 0 cost. Sample D, it's a prototype, 0 cost, and sample E. So the first sample is going to be removed from the priority query is going to be sample C because it has cost 0. It can be also sample D depending on the algorithm you use to add samples in the query. So basically then sample C is going to try to conquer the remaining nodes. Okay, like so for instance, what's going to be the cost that sample C, let's say it's going to be the cost that sample C is going to offer to A. Okay, as I told you, we are using the fmax, which means the cost is going to be the maximum value between the cost. I'm going to use this notation here, the cost of C and the distance between A and C. So it's going to be something like that. The cost of C is 0 because it's a prototype. The distance between A and C is 0.4. So the maximum value between 0 and dot 4 is going to be dot 4. So the cost that sample A is going to, sample C is going to offer to sample B is going to be dot 4. And then dot 4 is much better than a very high value. So the new cost of sample A is going to be dot 4. I'll just update here, dot 4. And now sample A is going to be conquered by sample C. Okay, by conquered, I mean sample A is going to receive the very same label, the yellow color of sample C. And then sample C is going to try to conquer sample D. That's the very same idea. I'm going to take the maximum value between the cost of C and the distance between C and B. That's 1.1. So 1.1 is much better than a very high value. Let's just update the priority query. Sample C is conquered. Sorry, sample B is conquered by C, and sample C is going to try to conquer D, but a prototype cannot conquer another one because we don't have arc weights with negative values. And then C tries to conquer E, and C offers dot 2.1. That's much better than this one. And by now, sample E has been misclassified. But it's not a big deal because the training step, it's not finished yet. Okay, so sample C has already tried to conquer all his neighbors, and then the very same process is repeated over again. Sample C can no longer play anymore. And then we're going to remove from the priority queue once more the sample with the lowest cost. It's going to be another prototype. So it's going to be D. So D is going to try to conquer all the samples of the graph once again. It's going to try to conquer, D is going to try to conquer sample C, but he cannot do that because he's a prototype. D is going to try to conquer sample B, and D offers the maximum value between 2.4 and 0 is 2.4, but 1.1 is much better than 2.4, so sample D cannot conquer B. The same happens with A. D offers the cost of 3.1, like the maximum value between 3.1 and 0. So, but 3.1 is worse than dot 4, so D cannot conquer A. But now D can conquer E because D is going to try to offer the cost dot 7 to E, and E has the cost 2.1, so it's much better dot 7. Remember, the main idea is try to minimize the cost of each sample. And then, oh sorry, I forgot to update the cost here, but it was 2.1, but now it is dot 7. Okay, so E has been conquered by sample D. That's okay? So, and then we just, D has tried to conquer all his neighbors, and the next sample to come out of the query is sample A because it has dot 4. Okay, so let's see if we can conquer anyone else here. So A tries to conquer C, but he cannot do that because it's a prototype. Tries to conquer E, but it offers the maximum value between dot 4 and 3.7, and is worse than dot 7. A tries to conquer D, but he cannot do that because D is a prototype. And finally, A tries to conquer B. So the cost that sample A is going to try to offer to B is basically the maximum value between the cost of A, that is dot 4, and the distance between A and B, that is dot 3. So the maximum value between dot 4 and dot 3 is going to be dot 4. So the new cost of sample B is going to be dot 4. Right? It's going to be dot 4. So B has been conquered now by sample E. So we need to just like remove this arrow here and make B to point to sample A. And then the last sample to come out of the query is sample B. and sample B tries to conquer all his neighbors again, but he cannot change the shape of the graph, and at the very end we have this optimum path forest. Okay, as I told you, the cost of the prototypes 0, 0, and the new cost of samples. Okay, sample A, sample B, sample C, sample D, and sample E. As I told you, at the very end of the training phase, we have a collection of optimum path trees, and these trees are rooted at the prototypes. Okay? By rooted, I mean if I take, like let's get it started. I can pick just any node from the training set, and if I follow the predecessor map, I mean if I follow the guy that has conquered someone else, I'm gonna end up the prototype. Okay, so basically that is the training phase of the OPF that uses the complete graph as the adjacency relation, the MSD to find out prototypes, and the Fmax as the path cost function. Okay, so and finally, with respect to the testing phase, so the main idea of the training phase is just to build the optimum path forest, and then the classification phase is going to try to do something very similar, and we're going to just put once more the name of the nodes here. So basically, I just pick a sample from the test set that every single training sample is going to try to conquer. It's going to try to offer two sample C's, for instance. But the cost that sample A is going to offer to T is just the maximum value. Remember, we're using Fmax. The maximum value between the cost of A, that is 0.4, and the distance between A and T, that is 0.7. So the cost that sample is going to offer to T is 0.7. The cost that sample T is the very same procedure. It's going to offer to T is basically the maximum value between 0.4 and 0.2. That's going to be 0.4. You know, 0.4 and 0.2. The cost that sample T is going to offer to T is the maximum value between 0 and 1.1. That's going to be 1.1 because C is a prototype. The cost that sample D is going to offer to T is the maximum value between 0, because D is a prototype, remember, and 0.3. It's going to be 0.3. And the cost that sample E is going to offer to T the maximum value between 0.7 and 0.6. That's going to be 7. So we just computed the cost that every single training node is going to offer to sample T. That's this sample here that's going to be classified. And then, as I told you before, the main idea of the OPF is try to minimize the cost of each sample. So at the end, we are going to choose the sample that offered the lowest cost. That is sample D. So basically, C is going to be conquered by sample D with the cost 0.3. Okay, so basically it's a kind of min max optimization problem, because we just compute the sample that each training sample is going to offer to sample T using the Fmax, but the training sample that finally conquers sample T is the one that offers the minimum value among all these costs, right? We're going to just pick a figure here that shows the final classification step. Okay, so I'm going to just put this guy over here, and then we have sample T labeled with the blue class. So, and then we're gonna move to the So as soon as we classify the sample, we're going just like to remove this sample from the graph, and then we pick the next testing sample, and we are going to do that for every single testing sample until we have gone off all these testing samples. Okay, so basically the main idea of the OPF, just to summarize what we have seen today, we have the OPF. We need to choose the adjacency relation. Here we use the complete graph. We need to choose a methodology to estimate prototypes, and we use the minimum spanning tree. And for the path cost function, we use the F max. OPF has a training phase. The training phase aims at, as we have seen, building the Optimum-Path Forest. So basically, we connect nodes using the Adjacency relation. We compute prototypes by means of the MST. Then we just execute the OPF algorithm, the competition process. And the output of the training phase is just the Optimum-Path Forest. And then for the testing phase, we just like pick a sample from the test set, we connect it to all training nodes, we compute the cost that each training node is going to offer to that testing sample, and then we pick the training sample that has offered the minimum costs. Okay, so that is the very first version of the OPF. If you are interested in using the OPF, you can just look for the lead OPF that's available in the internet. You can find it in my. You can find a link in my homepage, and then you can start using the OPF classifier. So that is it. Thanks for coming by, and if you have any questions, please just like drop me an email. Okay, thank you.